Hello everyone! Today's video is about RSA encryption, which is a classical method of encryption whose strength depends on the difficulty in prime factoring a very large number. Quantum technologies, which promise making the prime factorization of large numbers much easier, threatens the security of this encryption method. The idea is that Selwa, the sender, needs to send her message M to the receiver Reese securely. For it to be a secure method of communication, she cannot send M as is, but she has to encrypt it first and then send it to Reese, who at his end must decrypt what he receives to recover M. In the RSA method of doing things, letters and other characters are sent in their number representation. Assuming that each character is assigned a two-digit number to represent it, let's look at this example. The word hi followed by an exclamation mark. If 18 corresponds to uppercase H, 45 to lowercase I, and 62 to the exclamation mark, then M is given by this, and the receiver knows that to convert it back to proper characters, two digits have to be taken one at a time. But as we said earlier, M should not be sent directly in this form, but should be encrypted first, just in case it falls in the wrong hands before getting to Reese. To achieve that, at Reese's end, he chooses two very large and different prime numbers, P and Q. He multiplies them to get N. For this scheme to work, the message M has to be less than N. If it isn't, then M should be broken down into smaller parts, each less than N, and sent separately. Reese also chooses two more numbers, the encryptor E and the decryptor D. We will soon talk about how they are chosen. To the world, including Selwa, Reese makes N and E known. This gives all those who want to send him a secure message using the RSA method all the information they need. However, Reese keeps D secret. At her end, Selwa wants to send Reese the message M, and to encrypt it, she finds the remainder R such that M to the E is congruent to R modulo N. Then she sends R to Reese. Reese takes that information and uses the relation R to the D is congruent to M modulo N to recover the message M. The question is, how does Reese choose E and D? Well, they somehow have to depend on the prime numbers P and Q, who nobody should know about. Otherwise, they'll be able to decrypt the message. The central function is phi, evaluated here for n equals P times Q. It's the Euler function, and for our n here, it equals P minus 1 times Q minus 1. E is chosen so that it's relatively prime to phi of n. There will be more than one candidate for that. And D is chosen so that E times D is congruent to 1 modulo phi of n. Let's look at a numeric example. We will consider small values for P and Q to make it clearer how RSA encryption works. But remember, it's only secure when P and Q are too big to guess, which is how it is in real-life applications. Okay, so in this example, Reese chooses P equals 2 and Q equals 5. This gives n equals 10 and phi of n equals 4. In this case, he can choose E equals 3. And to satisfy this relation, he chooses D equals 3. To the world, Reese makes it known that n equals 10 and E equals 3. But he keeps D equals 3 secret from everyone. Selwa wants to send her message M equals 7. Using this relation, and since she knows N and E, which were made public, she solves for R in this fashion. She knows that 7 is congruent to minus 3 modulo 10, since 7 minus minus 3, which is 7 plus 3, is divisible by 10. She squares both sides of the relation to get this. She also knows that negative 3 squared is congruent to minus 1 modulo 10, since 9 plus 1 is divisible by 10. She combines these two to obtain 7 squared is congruent to minus 1 modulo 10. Then she takes that relation, combining the two by multiplying the corresponding sides to obtain 7 to the 3 is congruent to 3 modulo 10, so r equals 3, which she sends to Reese, who uses this relation to recover the message m equals 7. In today's exercise, you will justify the Euler function we used. For a positive integer m, the Euler function phi of m is defined to be the number of elements in the set of positive integers 1 to m minus 1 that are relatively prime to m. For example, if m equals 8, then in the set 1, 3, 5, and 7 are relatively prime to 8. So phi of 8 is 4. Hohenbauer